All right, welcome back everyone to The Deep Dive. You know how we do things around here? We roll up our sleeves, we grab some fascinating research, and we really try to unpack it. Today is no exception. We're taking a look at a brand new paper in machine learning and, well, the title is a mouthful, ForAug, recombining foregrounds and backgrounds to improve vision transformer training with bias mitigation.
Yeah, that's quite a title.
But it really gets to the heart of what they're trying to do here. You know, we're always talking about image classification. It's such a fundamental task in computer vision.
Right.
And we've seen this huge rise in vision transformers, these really powerful models, but they tend to be data hungry and can sometimes exhibit unwanted biases. So how do we make them better? Well, this paper by Tobias Christian Noun and their team from RPTU, Kaiser Slaughter, and Landau, and DFKI, proposes a really clever method to address this data challenge and the bias issue. They call it, like the title says, ForAug. It's all about augmenting our training data in a way that helps these vision transformers learn more effectively and generalize better.
Yeah, I mean, the implications of this are pretty significant. Think about all the applications of image classification, like medical imaging, self-driving cars, you name it. If we can make these models more accurate and less biased, it could have a real impact on how these technologies work in the real world.
Absolutely. And this paper really digs into the nitty-gritty of how they achieve this. They've even created a new data set called FourNet by applying this ForAug technique to ImageNet, which, for anyone who's not familiar, is like the gold standard data set for image classification.
Right. ImageNet is massive. It's been incredibly influential in the field. And the authors do a nice job of setting the stage by talking about, the historical context of image classification, how ImageNet has really driven progress. Then they get into the rise of these vision transformers.
Yeah, they kind of lay out this narrative of how we got here and why these vision transformers are such a big deal. But then they point out this key difference between vision transformers and the more traditional convolutional neural networks, or CNNs.
Yeah, it's all about translation equivariance. CNNs, by their very nature, they have this built-in ability to recognize an object regardless of where it is in an image. But vision transformers, they don't have that inherent property. They have to learn it from the data.
So that means we need to train them on data that explicitly shows these objects in all sorts of different positions and contexts, right?
Exactly. And that's where ForAug comes in. It's specifically designed to address this limitation by recombining foreground objects with different backgrounds to create this richer and more diverse training set.
It's kind of like, teaching a child to recognize a cat. You wouldn't just show them pictures of cats always sitting in the middle of a living room. You'd show them cats in trees, cats on beds, cats hiding under furniture.
Right. Cats in boxes, cats doing all sorts of cat things.
Exactly. And by giving the vision transformer this more varied visual experience, it can learn to generalize better and focus on the actual object, not just its surrounding context.
And the paper doesn't just stop at describing this idea. They really go in depth into their methods and experiments. They start by reviewing all the existing data augmentation techniques. Things like flipping an image, rotating it, adjusting the colors.
There's the classic stuff.
Right. But then they get into more recent and more sophisticated techniques like patch dropout and mix-up. And they explain how ForAug differs from these and other techniques like copy-paste, which is used more often in object detection. ForAug is really tailored for image classification.
And it uses this really neat trick of in-painting the background after they remove the foreground object. So it's not just a matter of, cutting and pasting things onto different backgrounds. They're creating a more realistic and semantically neutral background.
Yeah, and that's a really important detail. They want to make sure that the model isn't learning to rely on the background as a clue for classifying the object. They really want it to focus on the object itself.
So how does this ForAug actually work in practice? They call their method Recombined, and it seems to have these two main stages.
Yeah, there's an offline segmentation stage, and then there's an online recombination stage that happens during training.
Okay, so the segmentation part, that happens beforehand.
Yeah, that's where they take the original images and they separate the foreground object from the background. And they use a really sophisticated model for this called grounded SAM, which is based on these other really powerful models called grounding Dino and SAM.
And these are all cutting-edge models that have been trained on massive data sets, right?
Absolutely. These are not your run-of-the-mill image processing tools. They're really advanced. And what's really neat about grounded SAM is that it's prompt-based. So you can guide it by giving it text instructions.
So you could say, find me the dog in this image.
Yeah, exactly. Or even better, you could say, find me the dog, which is a type of mammal, They actually use WordNet, which is this huge lexical database, to create more robust and general prompts. This helps the model to identify and extract the foreground objects more accurately.
So they get this like a clean cutout of the dog.
Well, it's not always perfect. Sometimes the model might, miss a part of the dog, or it might include some of the background. So they have to do some additional processing to refine these masks, these outlines of the object. They actually extract multiple potential masks and then merge any that are too similar. It's all about getting the most accurate representation of the foreground object.
So once they have that foreground object, how do they fill in the background?
So they use a separate model for that, which is called an object removal model or an in-painting model. Their preferred choice is something called attentive eraser, which is really good at filling in the missing parts of an image in a way that looks natural.
It's like those photo editing apps that can remove unwanted objects from a picture.
Right. Exactly. This is the same kind of technology, but in this case, they're using it to create these clean backgrounds that they can then use for recombining with the foreground objects.
And they don't just randomly pair any foreground with any background, do they?
No, they're very deliberate about that. They actually use a scoring mechanism that involves an ensemble of pre-trained models, a VIT, a ResNet, and a Swin Transformer. So they're basically asking these models to evaluate how well each foreground-background pair works together.
So they're kind of like judges in a competition, rating each pairing based on different criteria.
Yeah, I like that analogy. They have this formula, equation 1 in the paper, that takes into account things like how well the foreground object is classified, how much the background distracts from the object, and the relative size of the object in the image.
Yeah.
And they have these parameters in the formula that they can adjust to fine-tune the selection process.
It's like they're optimizing for the best possible combinations to create the most effective training data.
Exactly. And then on top of all that, they filter out any backgrounds that are too synthetic looking. They don't want to introduce any artificial artifacts that could mislead the model.
So it's a very carefully curated data set, right?
It's not just a random jumble of images. It's very intentional.
Okay, so now they have all these foregrounds and backgrounds ready to go. What happens in the online recombination stage during training?
So this is where things get really interesting. For each foreground object, they randomly select a background to pair it with. And they experiment with different strategies for this selection. They might choose the original background or a background from the same class of objects, or even any background at all, just to introduce more diversity.
So like a dog could end up in a forest or on a beach or in a spaceship.
Yeah, pretty much.
Yeah.
And then they resize the foreground object based on its original size and the size of the foreground in the chosen background. And they even introduce some random variation in this resizing to make things even more unpredictable for the model.
So they're not just sticking a tiny dog in the middle of a huge forest, for example.
No, they're trying to make it look as realistic as possible. They even use a special distribution called a generalized Bates distribution to determine where to place the object within the background image. This allows them to control whether the object is more likely to appear in the center of the image or towards the edges, or uniformly across the image.
It's like they're thinking about all the different ways that an object might appear in a real-world scene, and they're trying to capture that variety in their training data.
Exactly. And then, to top it off, they apply a Gaussian blur to the edges of the foreground object's mask, that transparent boundary, to blend it seamlessly with the background. It's all about creating these really convincing composite images.
So they've put a lot of thought into how to make this augmented data as realistic and effective as possible.
Yeah, and they back it all up with rigorous experiments. They did a ton of ablation studies, which is where you systematically remove or change different components of the method to see how it affects the overall performance.
And they tested this ForAug technique on a smaller data set called Tiny ImageNet before scaling it up to the full ImageNet, right?
Right. Tiny ImageNet is like a miniature version of ImageNet. It's still a challenging data set, but it's much smaller. So it's easier to experiment with different things and get quicker results.
And what did they find in these ablation studies?
Well, they found that a lot of their design choices really do matter. Things like using general prompts for the segmentation, using attentive eraser for the in-painting, having a good range of foreground sizes, and using a cosine annealing schedule for mixing the FourNet data with the original ImageNet data. All of these things contribute to the overall effectiveness of the method.
So it wasn't just a matter of, throwing everything together and hoping for the best. They really had to fine-tune each step of the process.
Right. They also did some really interesting analysis on how different settings of the extended Bates distribution, which we talked about earlier for positioning the foreground object, affect performance. They found that a uniform distribution, where the object is equally likely to appear anywhere in the image, generally works best.
And they also compared the statistical properties of the original ImageNet dataset with their generated FourNet dataset.
Yeah, that's important because it shows that FourNet really does increase the diversity of the training data in terms of object-background relationships. Even though the total number of images in FourNet is slightly smaller than ImageNet, because sometimes the segmentation process fails, the variety of combinations is much greater.
So it's not just about quantity, it's about quality and diversity.
Absolutely.
Okay, but let's get to the million-dollar question. Does ForAug actually work?
Well, the short answer is yes, it does. They tested it on the full ImageNet dataset using a variety of different model architectures, including vision transformers, ResNets, and Swin Transformers.
And they found that training on FourNet consistently improved accuracy across all these different models.
Exactly. Now, the improvements were most significant for the larger vision transformer models, like VITL, which saw a boost of up to 4.5 percentage points. But even the ResNets, which are more traditional CNNs, saw some improvement, although it was more modest, around 1 percentage point.
So it's not just a vision transformer specific trick.
No, it seems to have broader applicability. And they even suggest that pre-training on FourNet can help to reduce overfitting, especially for those larger models.
So it's not just about squeezing out a few extra percentage points of accuracy. It's about making the models more robust and more generalizable.
Exactly. And they don't stop there. They also tested these FourNet trained models on a bunch of downstream tasks, which are basically more specialized image classification tasks. These included things like classifying different types of aircraft, cars, flowers, food, and even pets.
So like taking what they learned from ImageNet and applying it to more specific real-world scenarios.
Right. And on these downstream tasks, the FourNet trained models really shined, especially the vision transformers. They saw improvements of up to 7.3 percentage points. That's a pretty substantial gain.
It really suggests that FourNet is helping these models to learn more fundamental and transferable visual representations.
Yeah, I think that's a key takeaway here. It's not just about making the models better at classifying images from ImageNet. It's about giving them a more robust and generalizable understanding of visual concepts that they can then apply to other tasks.
And beyond just accuracy, this paper really emphasizes the use of ForAug for analyzing and mitigating model biases.
Right, and this is where the controlled nature of the FourNet dataset really comes into play. They can systematically manipulate the relationship between foreground objects and backgrounds to test how the models respond to these changes.
And they introduce these specific metrics to quantify different types of biases. Can you walk us through those?
Sure. So they have a metric for background robustness, which measures how much the model's performance changes when you switch from using only same-class backgrounds to using a variety of different backgrounds. Ideally, you want the model to be indifferent to the background, to really focus on the foreground object.
Makes sense. What about foreground focus?
That's where they use those really cool explainable AI techniques like GradCam and integrated gradients to visualize which parts of the image the model is paying attention to when making its prediction. They found that training on FourNet generally leads to models that are more focused on the foreground object, which is a good sign.
And they also have a metric for center bias, right? This is that tendency for models to focus too much on the center of the image.
Yeah, that's a common bias. And ForAug allows them to really test this by placing the foreground object in different locations within the image. They found that FourNet training significantly reduces this center bias, which again suggests that the models are learning to be more attentive to the entire image, not just the center.
And then there's the size bias, which I guess is about how the model handles objects of different sizes.
Right. And they found that FourNet trained models are more robust to changes in object size, meaning they can accurately classify an object, whether it's large or small, in the image.
So it's really a comprehensive approach to tackling these biases.
Yeah, they're hitting it from all angles, and I think that's really the main takeaway here. ForAug is not just a simple data augmentation trick. It's a powerful tool for improving the robustness, generalization ability, and fairness of image classification models.
And the authors even suggest that these ideas could be extended to other areas of computer vision, like video recognition or image segmentation.
Yeah, it's really exciting to think about the potential applications of this kind of approach.
Now for our Novel Notions segment, where we like to take a step back and think about the bigger picture, this whole idea of separating and recombining elements of a data sample, like they do with foregrounds and backgrounds and images, could this be applied to other types of data?
Ooh, that's a good one. What immediately comes to mind for me is audio data.
Oh, interesting. Right.
Yeah, think about it. Could we develop similar techniques to isolate, say, specific sounds from background noise, like separating a bird song from the rustling of leaves or traffic sounds?
And then recombining those isolated sounds with different background soundscapes.
Exactly. Imagine a ForAug dataset for audio event classification. We could train models to be much more robust to changes in background noise, which is a huge problem in real-world audio applications.
Like speech recognition in noisy environments.
Right.
Or identifying bird species from recordings taken in different habitats.
Right, exactly. And we could even adapt those bias metrics from the image domain to the audio domain. How much does a model rely on the background noise to identify a sound? Does it struggle to recognize sounds that are very short or overlap with other sounds?
It's like opening up a whole new avenue of research in audio processing.
Yeah, I think there's a lot of potential there. And, it doesn't stop at audio. What about text data?
For text.
Yeah, why not? Could we use large language models to, I don't know, maybe identify and extract key phrases or concepts from sentences, and then recombine them with different surrounding text to create this more diverse and challenging training data?
That's a fascinating idea. You could create a data set where, say, a sentence expressing a positive sentiment is embedded in contexts that are neutral or even negative.
Right, to train sentiment analysis models that are less susceptible to the influence of surrounding text. Or maybe you could train models to better understand the nuances of language and how meaning can shift depending on the context.
It's like teaching these language models to be more like human readers who can understand the subtleties of tone and implication.
Exactly. So even though this paper focuses on images, I think it opens up a whole new way of thinking about data augmentation and bias mitigation that could be applied to all sorts of different domains.
It's really about finding those fundamental building blocks of meaning in the data and then figuring out how to recombine them in creative and challenging ways to train more robust and generalizable models.
Well said. I think that's a great note to end on.
Yeah, I think so too. So for our listeners, if you're interested in digging deeper into this research, we'll be sure to include a link to the paper in the show notes. It's a dense read, but it's worth the effort. And in the meantime, keep exploring the fascinating world of machine learning research. There's always something new to discover.
Absolutely.
Until next time, happy deep diving.